Hi there. This video is going to walk through in more detail about the hydrogen atom wave functions and orbitals. So we've already seen that the full form of the hydrogen atom wave function is given by this expression here, where we have essentially a product of three functions, each of which depend on only one variable. So we have a function of r only, a function of theta only, and a function of phi only. And we've already encountered the theta and phi components of our wave function, so those are actually just our spherical harmonics. Okay, so this part we've already solved that in our rigid rotor model. So that just leaves us with one part of our function to figure out, which is the r of r component, and that is what we call our radial function. Okay, so going back to our Schrodinger equation for the hydrogen atom, hopefully this looks familiar, this giant equation we have seen before. Okay, so just taking this apart a little bit, we can see that we have terms that contain only the r component. So that term is just in terms of r. This last term here is only in terms of r. And then we have this middle term, which is our theta and phi. Okay, so this one is r, and theta and phi. So since the r and theta and phi variables are separated into their own terms, okay, that lends us to being able to use the separation of variables technique that we've used before. So if you think back to our wave equation or particle in a box solutions to the Schrodinger equation, those employed this same separation of variables technique. So it's the same thing that we've used before, okay, except now we're separating r from the angular parts, from the theta and phi parts of our equation. Okay, so moving through our separation of variables approach, just hitting the highlights there, what you would do is sub in for the wave function, okay, wherever you see your psi in that Schrodinger equation, okay, you'll plug in this expression of your r times your spherical harmonics. Okay, then divide by that and do a little rearranging, and you should end up with these two expressions that result. Okay, so one expression, we're basically isolating the theta and phi components of our equation, and then the other one will isolate all of the r or the radial components of our equation. So a good exercise would be to just pause the video for a few minutes and see if you can execute that rearrangement. So sub in this expression for your wave functions, okay, in this equation, and see if you can tinker around with that expression to end up with these two expressions. Okay, so what you'll end up with is that you'll have this expression essentially added to this expression to equal your 0. Okay, and then that tells you that you just have basically equal constants that are opposite in sign that add up to 0. Okay, so it's very similar to the process that we used for solving the spherical harmonics part. Remember, we did that individually, okay, where you had that constant m, that came into play. So you had parts of your expression equal to m or minus m for your separation constant. Okay, so take a minute, see if you can get to these two equations. Okay, so essentially what we've done here is separated our variables. All right, so assuming you had success with that exercise, again, we've already taken a look at the angular part. Okay, this is our rigid rotor exercise. Okay, this is where we got our spherical harmonics. Okay, that's an exercise that we've already gone through, so we're not going to do that again. And then that leaves us with our radial equations that we need to finish up with to get our full wave functions. Okay, so let's zero in on this radial equation. So we have one feature here that, again, because we've already solved the spherical harmonics, we already know what the value for beta is. Okay, so if you go back and look through your notes, you'll see that we've already determined that beta is equal to L times L plus 1, right, where L is our angular momentum quantum number that we've been using for the past couple of weeks. Okay, so all we're going to do is sub that value for beta into our equation. Okay, and again, do a little the magic rearranging. Okay, so maybe take a minute again, pause the video, see if you can plug in for your beta, the L times L plus 1, and then rearrange to get this final expression here. Okay, so this expression is what we define as the radial equation. Okay, so this is our equation of interest right now. Okay, so assuming that you feel comfortable with where that radial equation comes from, again, give that a try if you haven't already. When we solve that radial equation, it turns out that we end up with the requirement that we have quantized energy levels. So that expression for our quantized energy, okay, comes from solving that radial equation. Okay, we also get dependence on two quantum numbers. Okay, so we get dependence on the quantum number n. Okay, this looks familiar, hopefully, to you from your previous chemistry classes, and we've already looked at the hydrogen atom earlier in the semester. Okay, but this is essentially where the principal quantum number is born. Okay, it's born out of solving the Schrodinger equation for the hydrogen atom. Specifically, it's born out of solving the radial equation. Okay, and we also see that we get our angular momentum quantum number popping up here. So the radial functions that result from solving the radial equation will also depend on our angular momentum quantum number, and we see that we have a new restriction on our angular momentum quantum number that we did not have when we were using it in the context of a rigid rotor or our angular momentum. Okay, so that n-1 restriction, okay, again, is born out of solving the Schrodinger equation and solving the radial equation specifically for the hydrogen atom. Okay, so hopefully you noticed that this expression for energy that we have here, our quantized energy levels, that comes out of solving the radial equation, is exactly the same as what Bohr came up with when he was determining the quantized energy levels of the hydrogen atom. Okay, so remember Bohr obtained this expression basically through trial and error. He was like, hey, this quantization thing, if I include this integer, this integer n in my expression and quantize my angular momentum that I'm using to derive this equation, then it happens to work out, right? There was not really a better reason than that he had to put these equations together. Okay, so it's kind of nice that we have this beautiful cohesiveness to obtaining exactly the same expression that we know works from Bohr. Okay, we get that exact same expression by solving the Schrodinger equation. Okay, so I kind of skipped to the good stuff on solving that radial equation. It is a pretty tedious process. Okay, I'm not going to go through the details of that here. This is where we draw the line between being a chemistry class and not a math class. Okay, but I do have a handout that will be available to you if you're interested to see the details of solving that radial equation. So just keep an eye out for the handout if you want to see the nuts and bolts of solving that radial equation. Okay, so now we have kind of our complete picture of the hydrogen atomic wave functions. We've seen the derivation of a lot of equations and restrictions on our quantum numbers that we've been using for many years in our chemistry careers. Okay, so now you have an idea of where all of those rules and equations that you've been using a lot in your lives stems from. Okay, so let's take a look at the solutions to the radial equation. Okay, so these are what we call our radial functions. Okay, so these are the radial functions that we work with. So again, nothing really seems to get any simpler, does it, as we go along? But it's not too bad if we break it down. Okay, so we just have this combinatorial factor out front, okay, where we see the dependence on our quantum number n and quantum numbers n and l. Okay, so the principal quantum number and our total angular momentum quantum number. All right, and then we just have some an exponential term and a polynomial term. So this polynomial term here has a special name. This is referred to as the associated Laguerre polynomials. Okay, they're sometimes also just called the Laguerre polynomials. All right, so this equation will allow you to assemble the radial functions by hand if you ever find it necessary. Okay, but chances are you'll have the ability to just look them up in a table. Okay, so this is a table from an Atkins textbook. Okay, so just be aware when you look up these sorts of things in different resources, different textbooks, they're all going to have their own kind of characteristic format that's going to differ a little bit from source to source. Okay, so the thing that you want to pick out here, if you're using this table, is that you have this rho term in your expression, so make sure you go down here and figure out what rho represents for these functions. Okay, so again, don't get confused if you look at a different table and it's in a slightly different kind of format or they use different variables. Okay, they're going to end up giving you exactly the same result. Okay, so that's really it for our hydrogen atom wave functions. Okay, so these are the radial component of the wave functions, and then you would just couple these with your spherical harmonics. Okay, so then you have a table of your spherical harmonics, a table of your radial functions, and then usually there will be a table of them put together into what are called the hydrogenic wave functions. Okay, so again, just reminding you here, notice this says hydrogenic, okay, and notice the Z's, all right, so these are always going to be applicable, remember, to any one electron system. Okay, so we are focusing on hydrogen, okay, for the moment, but this would also be applicable to your helium plus, lithium 2 plus, so on and so forth. Okay, so any one electron system, and then you would just put in your corresponding atomic number. All right, so before we finish up here with our hydrogen atomic wave functions, let's take a look at the orthonormality conditions for these wave functions. Okay, so just like every other wave functions that we've looked at for other quantum mechanical systems, the hydrogen atom wave functions are also orthogonal and normalized. Okay, so let's practice setting up our different expressions that would correspond to those conditions. So first step will be to set up the normalization condition for the radial functions. Okay, so we're just taking that first part of our hydrogen wave function, just the radial part. Okay, so take a minute, pause the video, and see if you can put together the normalization condition that you would want to use for the radial function. So this is kind of a show that the radial functions are normalized kind of expression. Okay, so hopefully you've taken a minute to write your answer down for that. So let's see how you did. Okay, so hopefully this is the expression you came up with. Okay, chances are you may have forgotten the r squared there. Remember, the differential volume element for the radial component of our functions is r squared dr for the polar spherical coordinates. Okay, so don't forget to add in that extra r squared there. Okay, so next question for you is to set up the normalization condition for the full hydrogen atomic wave functions. Okay, so first one we just zeroed in on the radial functions. Now let's look at the normalization condition for the full hydrogen wave function. So here we want to include the spherical harmonics in our function. Okay, so take a minute, pause the video, and see if you can put together that normalization condition that we'd want to use for our full hydrogen atomic wave functions. Okay, hopefully you've taken the time to write an answer down for that. So let's double check how you did. Okay, hopefully you have an expression that looks similar to this. Yours might be in a slightly different order, different arrangement, okay, but as long as you have all of the main components there, that's all we're looking for. Okay, so I like to basically pull out all of the integrals and the corresponding differential volume elements out front just to clean it up a little bit. Okay, so that's why I have my radial integral here. Remember, limits there 0 to infinity, and then the differential volume elements for that, just like we had up here. And then we have our theta component. Remember, including our spherical harmonics here. So remember, theta ranges from 0 to pi. Okay, differential volume element, again, a little wonky for the theta. So we've got sine theta d theta for that differential volume element. And then finally our phi, okay, which is the nice one. It's just d phi for that differential volume element. And remember that phi ranges from 0 to 2 pi. Okay, and then we just plug in our psi star psi. Okay. All right, so hopefully that one went well. And then finally, let's take a look at our orthonormality condition for the full hydrogen atomic wave functions. Okay, so see if you can put together the orthonormality condition for the full hydrogen atomic wave function. So take a minute, try your hand at that, and then we'll check back and see how you did. All right, so let's see what you came up with. See how it matches this answer. Okay, so again, just bringing all of your integrals and differential volume elements out front here, so same as what we had up for our normalization condition. Okay, so what changes for the orthonormality condition versus our normalization that we had up top? Well, okay, remember orthonormality, you're concerned with, are these two functions that you're multiplying together the same, or are they different in some way? Okay, so normally we just have one index that we're worried about, so psi n versus psi m, okay, for a one-dimensional kind of wave function. It's nice and easy. Here it's a little bit more complicated. It looks a little bit messier because we have three different indices that we have to keep track of. Okay, so remember our functions depend on three quantum numbers, n, l, and m. Okay, so that means that we need to have that orthonormality condition for all three of those. Okay, so we would have psi star n prime l prime m prime times psi n l m. Okay, so that means that we have a Kronecker delta for n prime, where n can be equal to or not equal to n prime. Same for L. L can be equal to or not equal to L prime. And finally, the same for M, where M can be equal to or not equal to M prime. Okay, so just remember, if any one of these is not equal, okay, it doesn't matter if N equals N prime and L equals L prime, but M does not equal M prime, okay, then that whole thing equals 0. Okay, so it just takes one of these to spoil the bunch, okay? So all you're looking for are do your indices match up exactly or not, okay? So again, looks long and nasty at first glance, but it's really, once you kind of break it up into its components, hopefully it makes sense to you. Okay, so that is it for our general overview of the wave functions for a hydrogen atom and how we can put together some of those integral calculations that we will likely want to do in a lot of our calculations or orthonormality and normalization conditions. This is going to be the end of this part of the video, but keep an eye out for another video that walks through using these normalization and orthonormality triple integrals for those of you who would like a little bit more practice and information on those. All right. Thanks for listening. Hope this was helpful, and see you next time.